There's a sound in the universe few have heard, a deep, cosmic thud, like a drumbeat echoing across space and time. That's the moment two black holes, each heavier than stars, spiral together and collide. But here's the wild part. We can actually detect that collision from billions of light years away, not with telescopes, but by listening to the ripples it sends through the fabric of reality itself. These ripples are called gravitational waves, and they're rewriting everything we know about the cosmos. From hidden black holes to the echoes of the Big Bang, these invisible waves carry secrets about the most violent and mysterious events in the universe. And today, we're diving into 30 discoveries about them that will bend your mind like space bending around a neutron star. Buckle up, this is astrophysics like you've never experienced it before. For over a century, Einstein's theory of relativity told us gravitational waves should exist ripples in space-time caused by cosmic collisions, but no one had ever caught one in action. Until September 14, 2015. That's when the Laser Interferometer Gravitational Wave Observatory, or LIGO, picked up something extraordinary. A signal so faint it stretched and squeezed LIGO detectors by less than 1,000th the width of a proton, yet so powerful it came from two black holes smashing together over 1 billion light-years away. Scientists named this event GW15094, and what it revealed was breathtaking. Those black holes, each around 30 times the mass of our Sun, spiraled toward each other at half the speed of light before merging into one. The energy released in that collision, more than our Sun will emit in its entire 10 billion-year lifetime. And LIGO didn't just hear it, it proved Einstein right after 100 years, launching an entirely new way to explore the universe. No longer limited to light, we could now listen to space itself vibrating with the echoes of cosmic violence. This wasn't just a discovery, it was the birth of gravitational wave astronomy. But gravitational waves had even bigger surprises in store, ones we could see as well as hear. On August 17, 2017, LIGO and its European counterpart, Virgo, caught the tremors of a cosmic catastrophe unlike anything witnessed before. This time, the signal came not from colliding black holes, but from two neutron stars, city-sized remnants of dead stars, each so dense a single teaspoon would weigh 1 billion tons. Coded GW170817, this event sent ripples through space-time and unleashed a fireworks show across the electromagnetic spectrum. Telescopes worldwide swiveled toward the source, capturing the afterglow in gamma rays, X-rays, even visible light. For the first time in history, humanity witnessed the same cosmic event through both gravitational waves and light, a technique called multi-messenger astronomy. The payoff was staggering. We saw gold and platinum forged in the violent merger, solving a decades-old mystery about where heavy elements in the universe come from. The collision confirmed that neutron star smash-ups are cosmic factories, spraying precious metals across space. Even more jaw-dropping, the data revealed these two stars had been spiraling toward each other for 11 billion years before their final, luminous embrace. This wasn't just another detection, it was a Rosetta Stone moment, translating whispers of space-time into a vivid picture of how the universe builds itself. These black hole mergers aren't just cosmic spectacles, they're cosmic puzzles, rewriting what we thought we knew about how black holes live and die. Take the collision LIGO detected in 2015. Those 30 solar mass black holes shouldn't have existed according to many models. Stars that massive typically explode in supernova so violent they leave nothing behind, no black hole at all. Yet here they were, not one but two of these giants waltzing toward collision. Then came the real shocker. Data revealed some merging black holes spin wildly, like tops flicked by a giant finger, while others barely rotate at all. That split defied expectations. How could some black holes spin so fast while their siblings barely moved? Theorists scrambled. Maybe these black holes weren't born from single stars but formed through chaotic mergers in crowded star clusters where collisions spin them up like cosmic pinballs. Or perhaps their spins tell the story of violent pasts, with some being cannibalized and reshaped over eons. Every new merger adds another twist. In 2017, LIGO caught a pair of black holes where one was spinning backwards compared to their orbit, like a dancer pirouetting the wrong way mid-waltz. That shouldn't happen if they'd spent their lives peacefully orbiting one another. The conclusion: some black holes get thrown together late in life, strangers forced into a gravitational tango by pure chance. Each detection peels back another layer, showing us a universe far messier, far more unpredictable than textbooks ever described. These aren't just collisions, they're crime scenes, and the evidence keeps pointing to a cosmos that plays by rules we're only beginning to decode. Imagine a cosmic lighthouse spinning hundreds of times every second, bending space itself with each rotation. That's what a neutron star does when it's just slightly lopsided, maybe a bump the size of a sugar cube on its surface. Unlike the violent crashes we've heard so far, these spinning stars hum a quiet, steady tune in gravitational waves, like a tuning fork vibrating in the void. Scientists call this a continuous gravitational wave, and catching one would open a window into the most extreme matter in the universe, matter so dense it defies the laws of physics as we know them. But here's the challenge: these signals are incredibly faint, buried under a sea of noise. Detecting them is like trying to hear a single violin in a symphony orchestra from miles away. Teams comb through years of LIGO and Virgo data, looking for that telltale hum. The payoff: if we find one, we'll learn exactly how stiff or squishy neutron star crusts really are, whether they crack like crystal or bend like taffy under unimaginable pressures. Some theories even suggest their cores might contain exotic particles never seen on Earth, or rivers of pure quarks flowing beneath the surface. The hunt for these elusive waves isn't just about confirming theories, it's about pushing detector technology to its limits. Future observatories like the space-based LISA mission could listen for these whispers over decades, tracking slow changes as neutron stars gradually lose energy, spinning down one gravitational wave at a time. Each quiet pulse carries secrets about the most extreme laboratories in the cosmos, places where matter exists in states no experiment on Earth could ever recreate. And one day, when we finally catch that steady cosmic hum, it won't just be a detection, it'll be like putting a stethoscope to the heart of a neutron star, listening to the universe's most extreme physics in real time. Now let's turn back the cosmic clock, way back to the very beginning. Hidden in the faintest whispers of gravitational waves could be echoes from the universe's explosive birth. Scientists call these primordial gravitational waves, ripples etched into space-time during the Big Bang itself, when the entire cosmos expanded faster than light in a fraction of a second. Finding them would be like uncovering the universe's first baby photo, a blurry snapshot of reality just moments after it burst into existence. The theory of cosmic inflation suggests these waves should still ripple through space today, stretching and squeezing the fabric of reality like fingerprints left behind by creation. But detecting them, that's one of the toughest challenges in physics. These waves would be unimaginably faint after nearly 14 billion years, buried under cosmic noise from galaxies, black holes, even the afterglow of the Big Bang itself, the cosmic microwave background. Yet researchers are devising ingenious ways to listen. Some scour the microwave background for telltale swirls patterns that would mean primordial waves once passed through. Others dream of futuristic space detectors like the proposed Big Bang Observer, tuned specifically to hunt these ancient vibrations. If we ever catch them, the payoff would rewrite cosmology. Did the universe really inflate in that split-second frenzy? Are there other universes beyond ours, each with its own unique physics? These waves could hold answers, carrying secrets not just about how our cosmos began, but whether it's part of something even grander. The hunt continues not just for black holes or neutron stars, but for the faintest murmur from the dawn of time itself. Black holes come in two familiar sizes: stellar mass ones, born from dying stars, and supermassive beasts lurking in galactic centers. But what about the middle children? For decades, astronomers hunted for intermediate mass black holes, the missing link between these extremes. Then gravitational waves delivered the smoking gun. In May 2019, LIGO and Virgo caught a signal unlike any before. GW 190514. The ripple pattern revealed a collision where one black hole weighed in at 85 times the Sun's mass. That's not just big, it's impossible by traditional standards. Stars that massive should destroy themselves in violent explosions, leaving nothing behind. Yet here it was, merging with another black hole 66 times the Sun's mass to form an even larger monster, 142 solar masses. This wasn't just a detection, it was a cosmic identity reveal. Intermediate mass black holes do exist, and gravitational waves are exposing their birth certificates. Some might form from runaway mergers in dense star clusters, like snowballs gathering mass with each collision. Others could be ancient relics from the early universe, when conditions allowed gigantic stars to collapse straight into black holes without exploding. The implications ripple far beyond a single detection. If these mid-sized giants are common, they could be the seeds that grow into supermassive black holes, anchoring galaxies over billions of years. Every new signal peels back another layer, proving the universe favors variety, from featherweight black holes to middleweights now stepping into the spotlight. The Cosmic Family album just got a major update, and gravitational waves are turning the pages. Gravitational waves have shown us that black holes don't always play by the rules. Sometimes they form pairs so bizarre they defy expectations. Take the event GW 190512 detected in May 2019. This wasn't just another black hole merger, it was a cosmic odd couple. One black hole clocked in at nearly 30 times the Sun's mass, while its partner was a lightweight at just 8 solar masses. That extreme mismatch, a mass ratio rarely seen in nature, left scientists stunned. How could such an uneven pair form? Theories started flying. Maybe the smaller black hole was a latecomer, captured by the larger one in a crowded star cluster. Or perhaps it was born from a star that lost most of its mass before collapsing, creating this lopsided partnership. But the surprises didn't stop there. Some binaries show black holes spinning in wild, misaligned ways, like dancers twirling in opposite directions. Event GW 151226 revealed a pair where one black hole's spin was tilted almost perpendicular to their orbit, as if it had been knocked sideways by some ancient cosmic collision. These oddball pairs force us to rethink how black holes find each other. Instead of growing old together peacefully, many might meet in chaotic environments, dense star clusters or galactic centers, where gravitational encounters fling them into unexpected alliances. One thing's clear, the universe has a flair for drama, crafting black hole duos that challenge every model we've built. With each new detection, we're not just cataloging collisions, we're uncovering a cosmic soap opera of forced partnerships, violent pasts, and gravitational surprises. And the plot twists keep coming. One of Einstein's boldest claims was that gravitational waves don't just ripple through space, they race across it at the speed of light. But for decades, this remained a prediction without proof. Then came the neutron star collision of August 17, 2017, the cosmic event that changed everything. When LIGO and Virgo caught the gravitational wave signal, telescopes worldwide swung into action. They spotted the flash of light from the merger just 1.7 seconds after the gravitational waves arrived. That minuscule delay wasn't a fluke, it was a cosmic stopwatch. After traveling 130 million light-years, both signals reached Earth nearly simultaneously, with any difference too small to measure. The verdict: gravitational waves do move at light speed, just as Einstein foretold. This wasn't just about confirming a century-old theory, it ruled out entire branches of alternative physics. Some theories suggested gravity might have a hidden mass, slowing its waves down. Others proposed extra dimensions could subtly alter their speed. But nature delivered a clear answer. Spacetime's ripples obey relativity's strict speed limit, no exceptions. The neutron star collision did more than dazzle us with light and ripples. It became the ultimate physics lab, testing Einstein's framework across cosmic distances with precision no Earth-bound experiment could match. And once again, the universe whispered back, Einstein was right. For centuries, astronomers measured cosmic distances using light, redshifts, supernova, Cepheid variables. But light can be tricky, scattered by dust or distorted by galaxies. Enter gravitational waves, nature's ruler, stretching across the universe without interference. Here's how it works. When two black holes or neutron stars collide, their gravitational waves carry a unique signature, an imprint of their distance. Unlike light, these waves don't dim or scatter. They simply fade in a predictable way as space itself stretches. Combine this with the observed light from a neutron-star merger, and you've got something revolutionary, a direct, independent way to measure cosmic distances. This matters because right now, the universe is giving us mixed signals. Measurements of how fast it's expanding, the Hubble constant, don't agree. Some methods using nearby stars say one number, others studying the cosmic microwave background say another. The difference might seem small, but it's a crisis in cosmology. Gravitational waves could settle the debate. The neutron-star collision in 2017 gave us our first crack at this. By comparing its gravitational wave distance to the redshift of its host galaxy, scientists got a new Hubble constant value, one independent of traditional methods. The result, smack in the middle of the dispute, but with a twist. Early data suggests gravitational waves might favor the faster expansion rate. With each new detection, this cosmic ruler gets sharper. Future observatories like LISA could track mergers across billions of light years, mapping the universe's expansion like never before. No dust, no distortions, just pure space-time geometry whispering the truth about how fast everything's moving apart. What we're witnessing isn't just a new tool. It's a paradigm shift, turning the fabric of space itself into the most reliable measuring tape humanity's ever used. Right now, gravitational wave detectors like LIGO are tuned to catch collisions of stellar mass black holes, cosmic heavyweights a few dozen times the Sun's mass. But the universe has even bigger players lurking in the shadows, supermassive black holes, monsters millions or billions of times heavier than our Sun. These titans don't just sit quietly, they collide, shake galaxies, and send gravitational waves so powerful they could bend spacetime itself. The catch: their mergers happen in slow motion. Unlike stellar mass black holes that spiral together in seconds, supermassive duets take years or even decades to finally merge. That's why ground-based detectors can't hear them. Their signals are too low, like the deep hum of a cello drowned out by the screech of violins. But soon we'll have a front-row seat to these cosmic symphonies with LISA, the Laser Interferometer Space Antenna. Scheduled to launch in the 2030s, LISA will be the first gravitational wave observatory in space, with 3 spacecraft flying in perfect formation over 2 million kilometers apart. Free from Earth's seismic noise, its laser-linked triangle will catch waves with wavelengths so long they'd wrap around a planet, exactly the kind supermassive black holes produce. Imagine tracking 2 galaxies merging over eons, their central black holes circling closer until spacetime itself thrums with their final embrace, and the science. Unprecedented, these mergers could reveal how galaxies grow, why supermassive black holes exist at all, and whether Einstein's gravity holds true in the most extreme regimes. Some theories even suggest spacetime might ring differently around these giants, hinting at new physics. Every ripple will carry clues about the universe's largest structures, and Lisa will be listening, turning whispers from the abyss into a new chapter of cosmic discovery. Black holes and neutron stars might be the usual suspects when we listen to gravitational waves, but what if the universe has stranger objects hiding in the shadows? Enter exotic compact objects, cosmic oddities so bizarre they blur the line between science and speculation. Picture a star made not of atoms, but of mysterious particles called bosons, holding itself together through quantum fuzziness instead of gravity. Or imagine a quark star, a neutron star's extreme cousin where crushing pressures dissolve matter into a soup of raw subatomic ingredients. These objects tease physicists because they might mimic black holes or neutron stars in their gravitational wave signals, but with subtle, telltale differences. When two boson stars collide, their waves could reveal faint echoes, like ripples bouncing off their almost transparent surfaces. Quark stars might produce unique frequency patterns when they merge, a cosmic fingerprint of matter pushed beyond neutronium into something even stranger. The challenge, spotting these tiny deviations in the data, like distinguishing two nearly identical songs played at a crowded concert. The hunt isn't just about adding to the cosmic zoo. If we found a boson star, it could mean certain dark matter candidates are real particles that barely interact with light but shape the universe invisibly. Quark stars would rewrite the rules of nuclear physics, proving matter can surrender to even more extreme states. Every gravitational wave signal is now a treasure hunt, sifting through the noise for hints of the truly exotic. And if we ever catch one, it won't just be a new discovery, it'll be proof that the universe's strangest inventions are out there, waiting to shake spacetime in ways we've only dreamed of. Close your eyes and imagine standing by the ocean, listening to the distant roar of countless waves crashing together, a sound so vast you can't pick out any single splash. Now picture that same phenomenon playing out across the universe, but instead of water, it's gravitational waves. A cosmic hum from millions of black hole mergers, neutron star collisions, and other violent events too faint to detect individually. Scientists call this the gravitational wave background, and it's one of the most elusive signals in the cosmos. Unlike the sharp chirps from single collisions we've detected so far, this background is a messy orchestra of overlapping ripples, all whispering at once. To find it, researchers don't just listen for one wave, they search for a statistical pattern buried in years of detector noise, like picking out a faint melody from a room full of static. The challenge: this signal is unimaginably subtle. Imagine trying to hear a single conversation in a stadium packed with cheering fans, yet the payoff would be monumental. Detecting this background could reveal the collective heartbeat of every black hole merger in history, events too distant or weak to spot alone. Some models suggest it might even hide traces of cosmic strings, hypothetical defects in spacetime left over from the Big Bang. Others think it could expose a population of primordial black holes, ancient relics from the universe's first moments. Right now, collaborations like NanoGrav are using pulsars, super-precise cosmic clocks, to hunt for this background. As gravitational waves pass between us and these spinning stars, they subtly alter the pulse's timing, creating a detectable pattern over decades. Meanwhile, next-gen detectors like LISA and the Einstein telescope will tune into lower frequencies where the background might sing louder. This isn't just about adding another discovery to the list, it's about eavesdropping on the universe's hidden chorus, a symphony of space-time woven from every collision we can't yet see. And when we finally hear it, the hum might tell us more about the cosmos's chaotic past than any single explosion ever could. Einstein's theory of general relativity has ruled supreme for over a century, shaping our understanding of gravity, black holes, and the cosmos itself. But like any good scientific theory, it needs to be pushed to its limits, and gravitational waves are the ultimate stress test. Every time two black holes collide or neutron stars spiral together, they create a laboratory more extreme than anything we could build on Earth, probing gravity in ways previously unimaginable. Take the gravitational wave signal GW150914. When LIGO detected this black hole merger, scientists scrutinized the ripples for any tiny deviation from Einstein's predictions. According to relativity, the waves should follow a precise pattern as the black holes spiral inward, merge, and then ring down like a struck bell. Remarkably, the signal matched Einstein's equations to within 99.9% accuracy, even in this realm of warped spacetime and crushing gravitational forces. But the most brutal tests come from neutron star collisions. These dense stellar corpses pack a sun's worth of mass into a city-sized sphere, creating gravity so intense that alternative theories predict subtle differences in how their gravitational waves behave. Yet again, relativity holds firm. The waves from GW170817 marched in lockstep with Einstein's math. Even more telling, the fact that gravitational waves and light from that event arrived within seconds of each other after traveling 130 million light-years, confirming another key prediction. Gravity moves at the speed of light, no faster, no slower. Still, the hunt for cracks in relativity's armor continues. Some theories suggest that under even more extreme conditions, like near the event horizon of a rapidly spinning black hole, tiny deviations might lurk. Future detectors like the Einstein telescope or space-based LISA will listen for these whispers of new physics, searching for anomalies in the waveforms or unexpected echoes. If they find even the slightest mismatch, it could open doors to theories beyond Einstein quantum gravity, extra dimensions, or something entirely unforeseen. For now, relativity stands triumphant, its equations unscathed by the most violent events in the universe. But with every new gravitational wave detection, we're not just confirming Einstein's genius, we're stress testing the very framework of reality, probing for the moment when gravity finally reveals its secrets. And whether relativity holds or finally falters, the answers will rewrite physics itself. Black holes don't just appear out of nowhere, they're born from chaos, forged in the fires of dying stars or violent cosmic encounters. But here's the twist: gravitational waves are revealing that these dark giants take wildly different paths to existence. Some grow up in quiet isolation, others are thrown together in gravitational bar fights. And the ripples they leave behind, they're like cosmic fingerprints telling us exactly how they came to be. Take the black hole pairs we've detected so far. Some, like GW150914, show nearly identical masses and aligned spins, the hallmark of a peaceful upbringing. These likely started as twin stars born together in a stellar nursery, living side by side for millions of years before collapsing into black holes that continued their silent dance. Their gravitational waves carry the rhythm of a long, steady relationship. No surprises, no drama. But then there are the rebels. Events like GW190412 feature wildly mismatched masses, with one black hole several times heavier than its partner. Their spins all over the place, some tilted, some even backwards. These aren't star-crossed lovers, they're strangers flung together by chance, likely meeting in the chaos of dense star clusters where gravitational encounters play matchmaker. Imagine two solo dancers at a crowded party, suddenly grabbed and spun into a duet by invisible hands, and the wildest part, some black holes might never have been stars at all. The detection of intermediate mass black holes like the 85 solar mass beast in GW190514 hints at a darker origin story. Could they be ancient relics forming directly from collapsing gas clouds in the early universe, or the result of black holes merging again and again, like snowballs gathering mass in a cosmic avalanche? Every collision we detect adds another piece to the puzzle, painting a universe where black holes form in ways we're only beginning to map. Whether born in solitude or forged in chaos, their gravitational waves are rewriting the story of how darkness takes shape in the cosmos, one ripple at a time. When two neutron stars collide, they don't just send ripples through space-time, they crack open a window into the most extreme matter in the universe. Inside these city-sized stellar corpses, matter gets squeezed to densities so absurd that a single sugar cube's worth would weigh more than Mount Everest. And gravitational waves, they're our only way to peek inside. Here's why these mergers are so revealing. As neutron stars spiral toward collision, their immense gravity distorts each other's shapes, creating subtle imprints in the gravitational waves they emit. The way they deform, whether they squish like marshmallows or resist like diamonds, depends entirely on their internal physics, governed by something called the equation of state. This isn't just a fancy term, it's the rulebook for how matter behaves under pressures that would vaporize Earth in a nanosecond. The big surprise from GW 170817. The data suggested neutron stars are stiffer than many models predicted. Instead of collapsing instantly into a black hole after merging, they lingered momentarily as a hypermassive neutron star, a fleeting, unstable monster dancing on the edge of oblivion. That delay told us their interiors might contain exotic particles or phases of matter we've never seen, like free-floating quarks or bizarre superconductors. Future detections could settle the debate. A softer equation of state would mean neutron star cores are more like cosmic jelly, easily deformed, a stiffer one. That might hint at undiscovered forces holding matter together against all odds. Each new merger tweaks the parameters, bringing us closer to solving one of physics' greatest mysteries: what happens to matter when gravity wins and the very idea of empty space ceases to exist. Most gravitational wave signals we've detected so far rumble through space at frequencies we can almost hear, like the deep thud of a bass drum. But what if the universe also hums with ultra-high-frequency ripples, trillions of times higher than anything our current detectors can catch? These could be the cosmic equivalent of a dog whistle, pitched so high it's utterly silent to our ears, but they might carry whispers from realms we've never seen. The hunt for these elusive high-frequency waves takes us into speculative territory where physics brushes against science fiction. One tantalizing source could be cosmic strings, hypothetical cracks in spacetime left over from the Big Bang, thinner than an atom but stretching across the universe. If these strings exist, their vibrations might send out bursts of high-frequency gravitational waves each time they snap or tangle. Another possibility: quantum fluctuations in the very early universe, magnified by rapid inflation into detectable ripples. The challenge is monumental. Unlike LIGO kilometer-scale detectors, catching these waves would require instruments sensitive to vibrations smaller than an atomic nucleus. Some proposed designs use ultra-cooled crystals or clouds of quantum-entangled atoms, tuned to resonate when these high-frequency ripples pass through. It's like trying to measure the weight of a snowflake using a scale built for elephants, but the payoff could redefine physics. Imagine decoding gravitational waves from the universe's first trillionth of a second, a time so early even light couldn't traverse the cosmos yet. Or proving the existence of cosmic strings, relics from when spacetime itself crystallized into its current form. These high-frequency whispers might be the only traces of phenomena that shaped reality but vanished without a trace until now. While current technology isn't quite there yet, the race to listen to gravity's highest notes is already reshaping how we think about the invisible fabric of existence. And if we succeed, it'll be like discovering an entirely new spectrum of sound in a universe we thought we knew. Gravitational waves don't just ripple through space, they twist through it, carrying hidden clues about the very nature of gravity itself. Imagine tossing a pebble into a pond and watching the ripples spread outward. Now picture those ripples having a subtle spin to them, some moving up and down, others side to side, even twisting in spirals. That's polarization, and for gravitational waves, it's a goldmine for testing whether Einstein's theory of gravity is the full story, or if something stranger lurks beyond. Here's why this matters. General relativity predicts gravitational waves should have just two polarization modes, like a cosmic plus and cross pattern stretching space in perpendicular directions. But alternative theories, like some versions of string theory or modified gravity, suggest there could be up to 6 possible polarizations, including ones that make space twist like a corkscrew. Detecting even a hint of these extra modes would shake the foundations of physics, pointing to forces or dimensions Einstein never imagined. The challenge. These polarization signals are incredibly subtle, buried in the noise of collisions, but next-generation detectors like the Einstein telescope or space-based LISA will have the precision to spot them. Think of it like upgrading from a blurry black and white photo to a high-resolution 3D movie. Suddenly, we'll see not just that space-time ripples, but how it ripples in exquisite detail. Already, there are tantalizing hints. Some analyses of LIGO data show tiny anomalies in how black hole mergers polarize space-time deviations too small to confirm yet, but enough to keep theorists awake at night. If future observations prove these aren't just glitches, we might be staring at the first cracks in relativity's armor, evidence of gravity behaving differently in the most extreme corners of the cosmos. This isn't just about adding another footnote to Einstein's legacy. Polarization could reveal whether gravity connects to hidden quantum forces, if extra dimensions curl unseen around us, or even how spacetime itself emerged from the Big Bang. Every ripple we catch isn't just a signal, it's a message, written in the twisting fabric of reality, waiting to be decoded. Gravitational waves might be revealing more than just black holes and neutron stars. They could be our first clue to solving one of cosmology's greatest mysteries, dark matter. That invisible stuff making up 85% of the universe's mass has eluded detection for decades, but now ripples in space-time are offering fresh leads. Take primordial black holes, hypothetical relics from the Big Bang, some no heavier than an apple. If these tiny, ancient black holes swarm through space, they could actually be dark matter. When they collide, they'd emit gravitational waves far quieter than LIGO usual detections, but future observatories might catch their whispers. A single confirmed signal would rewrite history, proving dark matter was hiding in black holes all along. Then there's the stranger possibility, dark matter particles interacting through unknown forces. While they barely nudge ordinary matter, some theories suggest dense clouds of dark matter could warp space-time around neutron stars, subtly altering their gravitational wave signatures. It's like hearing a violin play slightly out of tune, not enough to ruin the melody, but enough to hint something unseen is tugging at the strings. The hunt isn't just theoretical. Teams are already sifting through LIGO data for anomalies, unexpected glitches in black hole collisions or neutron star mergers that might betray dark matter's presence. Even a single outlier could point to particles or objects beyond our current physics. Whether it's primordial black holes or invisible particles bending gravity's rules, gravitational waves are turning into dark matter's newest interrogation room. And if these ripples ever catch a confession, it won't just solve a cosmic whodunit, it'll expose the hidden architecture of the universe itself. Black holes aren't just cosmic vacuums. They're the ultimate battlegrounds where gravity and quantum mechanics clash, and gravitational waves might finally help us spot the fallout. In the final moments of a black hole merger, as the newborn singularity settles into its quiet, dark equilibrium, some theories suggest spacetime doesn't just ring down smoothly, it stutters. Faint echoes could linger in the gravitational wave signal, like whispers bouncing off a quantum foam surface we can't yet see. This idea hinges on a radical notion that at the tiniest scales, spacetime isn't smooth but pixelated, a seething froth of quantum fluctuations. If true, a black hole's event horizon might not be the clean boundary relativity predicts. It could be a fuzzy, vibrating membrane, imprinting subtle glitches in the gravitational waves as they escape. Detecting these anomalies would be like finding scratches on a perfectly polished mirror, evidence of a deeper structure lurking beneath. Not everyone's convinced. Mainstream relativity insists black holes should ring down cleanly with no after-echoes, but alternative theories like loop quantum gravity or string theory leave room for these quantum tremors. The challenge: these signals will be buried in noise a million times fainter than the main collision. Future detectors like the Einstein telescope could change the game, with sensitivity sharp enough to catch these whispers if they exist. Imagine the implications. A single anomalous echo could reveal how spacetime really behaves at Planck-scale densities, bridging the gap between Einstein's gravity and the quantum world. It might even hint at what replaces the singularity: a wormhole, a bubble of new physics. Every black hole merger isn't just a collision, it's a high-stakes experiment probing the universe's most fundamental rules. And if those echoes ever surface, they won't just rewrite textbooks, they'll crack open a door to a theory of everything. Right now, we're only catching the loudest crashes in the cosmic symphony, the black hole mergers that shake spacetime hard enough for our detectors to hear. But this is just the opening act. The next few decades will see gravitational wave astronomy leap forward like never before, with a new generation of observatories pushing the boundaries of what we can detect. Picture this: detectors 10 times more sensitive than LIGO, like the planned Einstein telescope, buried deep underground to escape Earth's vibrations. With this kind of power, we could spot neutron star collisions every week instead of every few years. Even quieter events, black holes merging in the earliest epochs of the universe, or the faint hum of solitary neutron stars, would step into the spotlight. It's like upgrading from grainy home video to Ultra HD, revealing details we never knew existed. Then there's space-based detection. Missions like LISA, a trio of satellites flying in perfect formation, will open an entirely new gravitational wave frequency window. Imagine tracking supermassive black holes spiraling together for years before their final, thunderous collision. These titans don't just shape galaxies, they are the architects of cosmic structure. LISA could catch their mergers across the entire universe, mapping how these giants grew and evolved over billions of years. But the real game changer: combining gravitational waves with other cosmic messengers on an unprecedented scale. Future networks might include neutrino detectors, next-gen telescopes, and AI-driven alert systems, all working in sync. A single neutron star collision could trigger instant observations across every wavelength: gamma rays, radio waves, even neutrinos, painting a complete picture of these cataclysms in real time. And lurking in all that data could be the biggest surprises of all: signals that don't match anything in our current playbook, maybe echoes from cosmic strings, or traces of wormholes, or something entirely unexpected. Gravitational wave astronomy isn't just evolving, it's rewriting itself with every new discovery. The detectors of tomorrow won't just listen to the universe. They'll hear it thinking out loud. Detecting the faintest whispers of the universe requires more than just sensitive ears. It demands engineering so precise it borders on science fiction. LIGO detectors aren't just machines, they're time-traveling storytellers, capturing signals from black holes that shook the cosmos before dinosaurs even walked the Earth. And they do it by measuring movements tinier than anything in human experience, shifts in spacetime smaller than 1/10,000th the width of a proton. To grasp how absurdly precise this is, picture scaling the distance from Earth to the nearest star down to the thickness of a human hair. Now imagine detecting a change along that hair thinner than a single atom. That's the level of sensitivity LIGO achieves daily. Its laser beams race down 4-kilometer-long vacuum tunnels, bounced between mirrors so perfectly polished that any surface bumps are smaller than a single hydrogen atom. Even seismic vibrations from ocean waves or passing trucks could drown out gravitational waves. so the entire system floats on a complex suspension of pendulums and magnets, isolating it from Earth's constant trembling like a feather balancing on a breath. But here's the real genius. LIGO doesn't just listen passively. It uses quantum tricks to outsmart nature itself. By squeezing light into special quantum states, physicists reduce the inherent fuzziness of laser photons, pushing past what should be an unbreakable limit called the quantum noise barrier. It's like trying to hear a whisper in a hurricane, then inventing a way to mute the storm itself. This isn't just technology, it's alchemy, turning vibrations too small for words into a chorus of colliding black holes, neutron stars, and maybe one day, things we haven't even dreamed of yet. Every detection is a victory not just for astrophysics, but for human ingenuity, proof that with enough creativity, we can eavesdrop on the universe's quietest conversations. Gravitational wave astronomy isn't a solo act, it's a global symphony with detectors across continents working in perfect harmony. While LIGO might grab the headlines, its partners Virgo in Italy and Kagra in Japan are the unsung heroes sharpening our cosmic hearing. Together, they don't just detect ripples in space-time, they pinpoint exactly where those ripples come from, turning vague rumbles into precise celestial addresses. Here's why that teamwork matters. When LIGO catches a gravitational wave alone, it's like hearing a phone ring in a dark room. You know something's there, but you can't tell where. Add Virgo's third detector in Europe, and suddenly you can triangulate the sound, narrowing the source's location from a patch of sky the size of 1,000 full moons down to just a few dozen. That's how we spotted GW170817, the neutron star collision that set telescopes worldwide into a mad dash toward its galaxy. Then there's Kagra, nestled deep inside a Japanese mountain. Unlike LIGO and Virgo, it operates at cryogenic temperatures, chilling its mirrors to near absolute zero to reduce thermal noise. While still ramping up sensitivity, its unique orientation adds another critical angle to the network, helping distinguish genuine cosmic events from earthly tremors. But the real magic happens when all three detectors lock onto the same signal. With their combined data, scientists can measure the wave's polarization, test Einstein's theories with razor-sharp precision, and even gauge the tilt of black holes' spins relative to their orbits. It's like upgrading from a blurry snapshot to a 3D movie suddenly. Every collision tells a richer story. This isn't just about more detections, it's about better science. Each observatory's geographical spread ensures no single region's seismic noise or weather can blind the entire network. When one detector goes offline for upgrades, the others keep listening, making gravitational wave astronomy a round-the-clock endeavor. And as more join the hunt, like India's planned LIGO India, the cosmic web of ears will only grow sharper, turning whispers from the abyss into a chorus we can finally understand. While LIGO and Virgo catch the high-pitched chirps of stellar mass collisions, an entirely different approach is tuning into the universe's deepest bass notes. Meet pulsar timing arrays, cosmic metronomes that might be picking up the steady hum of supermassive black holes dancing in slow motion across the cosmos. These aren't your ordinary detectors. Instead of lasers and mirrors, they rely on pulsars, dead stars spinning hundreds of times per second, flashing beams of radio waves with the precision of atomic clocks. When gravitational waves pass between Earth and these distant lighthouses, they stretch and squeeze spacetime ever so slightly, making the pulses arrive a fraction of a second early or late. The trick, monitoring dozens of pulsars for years, even decades, to catch that subtle drift buried in the noise. What they're listening for is monumental, the combined rumble of every supermassive black hole pair in the universe. Unlike LIGO's sharp bursts, these waves are vast and sluggish, with wavelengths so long they could span the entire solar system. Imagine two black holes, each billions of times heavier than the Sun, circling each other for centuries as they gradually spiral inward, their gravitational waves vibrating spacetime like the lowest note on a cosmic cello. Recent data from collaborations like Nanograv has teased something extraordinary, a faint, common signal across multiple pulsars that might be the first hints of this background hum. While not yet confirmed as gravitational waves, the patterns match predictions eerily well. If verified, it would mean we've tapped into a chorus of black hole duets, each one the engine of a distant galaxy, slowly winding down toward an eventual collision that will shake the universe. This isn't just about adding another frequency to our gravitational wave playlist. Pulsar timing could reveal how galaxies merge over cosmic time, whether supermassive black holes always find partners or if some get stuck in eternal orbits. It's a patient, painstaking hunt, one that measures time in decades, not seconds, but the payoff would be hearing the universe's oldest, heaviest heartbeat. And when that rhythm finally emerges from the noise, it won't just be a detection, it'll be the soundtrack to how galaxies live, dance, and die. Think of gravitational wave detectors like cosmic census takers. Each time they catch a collision, they're adding another entry to an ever-expanding catalog of the universe's most violent events. Back in 2015, spotting a single black hole merger was front-page news. Today, scientists are analyzing dozens of these events, piecing together patterns that reveal the hidden lives of compact objects across the cosmos. Take black holes, for example. Early catalogs showed most merging pairs were between 20 and 40 times the Sun's mass, already puzzling since stars that big weren't supposed to leave behind black holes at all. But as more detections rolled in, outliers emerged. The 2019 catalog included a merger where one black hole clocked in at a staggering 85 solar masses, defying conventional star death models. Meanwhile, other entries featured featherweight black holes barely 6 times the Sun's mass, raising questions about how such small objects form. The data paints a picture of a universe far more creative and chaotic than we imagined, where black holes come in every size imaginable. Neutron stars tell their own story. Before gravitational waves, we only knew of isolated neutron stars or quiet binaries. Now, catalogs reveal their mergers are surprisingly diverse. Some involve perfectly matched pairs, while others, like GW190425, showcase bizarre mismatches where one neutron star is nearly twice as massive as its partner. These odd couples hint at violent pasts, possibly involving stolen matter or traumatic stellar encounters before their final collision. But the real power of these catalogs lies in the statistics. With enough events, patterns emerge, like how often black holes pair up versus neutron stars, or which environments spawn the most mergers. Already, the data suggests dense star clusters might be black hole matchmakers, while isolated neutron star pairs take billions of years to spiral together. Future catalogs, swelling with hundreds of detections, could finally answer whether black holes grow primarily through mergers or if some are born big, solving mysteries that light alone could never crack. What started as a trickle of discoveries has become a flood, each new entry a clue in the universe's grand puzzle. And with every addition, we're not just counting collisions, we're mapping the hidden demographics of darkness itself. After the chaos of a black hole collision, something extraordinary happens. The newborn black hole doesn't just sit quietly. It rings. Like a bell struck by a hammer, it vibrates in precise tones, sending out gravitational waves that reveal the very fabric of spacetime is singing. Scientists call this the ring-down phase, and it's one of the purest tests of Einstein's theory ever found. Here's how it works. When two black holes merge, the resulting monster isn't perfectly smooth. It's warped, distorted, like a drop of water wobbling as it falls. But gravity hates imperfections. Within milliseconds, it smooths the black hole's surface by radiating away these distortions as gravitational waves. The frequencies of these waves aren't random. They follow an exact mathematical pattern dictated by the black hole's mass and spin, a cosmic fingerprint encoded in spacetime itself. The real magic, these ring-down waves are independent of how the black holes collided. Whether they spiraled in gracefully or smashed together chaotically, the final tones depend only on the merged black hole's properties. It's as if the universe hits a cosmic reset button, erasing the details of the collision and leaving behind only the pure tones of the black hole's identity. For physicists, this is a golden opportunity. By analyzing these gravitational wave echoes, they can test whether black holes truly behave as Einstein predicted, or if subtle deviations hint at new physics. Some theories suggest quantum effects near the event horizon might tweak the ring-down frequencies, like a bell made of an unknown material chiming slightly off-key. So far, every detection matches relativity's predictions within razor-thin margins, but future detectors could spot anomalies hidden in the noise. This isn't just about confirming old ideas, it's about listening to spacetime's natural frequencies, the soundtrack of black holes settling into their final, silent forms. And with each new merger, we're not just hearing the universe's loudest crashes, we're eavesdropping on the quiet afterglow where gravity itself hums its truest notes. Picture this, a black hole so massive it warps not just light, but the very fabric of space-time itself, bending gravitational waves like a cosmic magnifying glass. Astronomers call this phenomenon gravitational lensing, and while we've seen it distort light for decades, the idea that it could twist gravitational waves too. That's rewriting the rules of detection. Here's what makes this so wild. When gravitational waves pass near a colossal object, like a galaxy cluster or supermassive black hole, space-time curves around it, potentially splitting the signal into multiple copies or even amplifying it, just like a lens focuses light. Imagine hearing the same black hole collision twice, milliseconds apart, as the waves take different paths around the cosmic lens, or catching a normally faint signal boosted to crystal clarity by the universe's own amplifier. The kicker, we might have already recorded lensed waves without realizing it. Some signals in LIGO catalog show odd quirks, extra spikes in the data or waveforms that seem slightly stretched. Could these be hints of lensing? Teams are racing to find out, combing through past detections for echoes or distortions that match theoretical predictions. If confirmed, lensed waves would be a game changer. They'd let us map the distribution of invisible mass in the universe, dark matter, rogue black holes, entire galaxies hiding in plain sight, by how they warp passing ripples. Plus, these cosmic mirages could magnify waves from the earliest black holes, ones so distant they'd normally be inaudible. It's like turning the universe's biggest obstacles into our most powerful tools. The hunt is on for that first unmistakable lensed signal, and when we find it, we won't just be listening to space-time's ripples, we'll be seeing how the cosmos bends them, revealing hidden structures no telescope could ever spot on its own. Deep beneath the Antarctic ice, another cosmic messenger is being hunted, one that could team up with gravitational waves to reveal the universe's most explosive secrets. High-energy neutrinos, ghostly particles so elusive they pass through entire planets without a trace, might hold the key to understanding what happens after black holes and neutron stars collide. And when these nearly massless particles arrive at Earth alongside gravitational waves, it's like getting two halves of the same incredible story. For decades, neutrino detectors like IceCube have scanned the skies for bursts of these mysterious particles, often tracing them back to violent cosmic engines like supernova or active galactic nuclei. But the real jackpot would be catching neutrinos and gravitational waves from the same cataclysm, a one-two punch of multi-messenger insight. Imagine a neutron-star merger producing not just ripples in space-time, but also a flood of neutrinos as matter is torn apart at unfathomable densities. That combined signal could tell us exactly how these collisions forge heavy elements or launch particle jets at near light speed. The search is already yielding tantalizing hints. In October 2019, just hours after LIGO detected a possible neutron-star collision, IceCube spotted a high-energy neutrino from roughly the same patch of sky. While not conclusive, the coincidence sent theorists into overdrive. Was this a cosmic double feature or just luck? Future detectors, like the planned Ice Cube Gen 2, could settle the debate with 10 times the sensitivity, turning coincidences into certainties. But here's the twist. Some theories suggest black hole mergers might also produce neutrinos, despite their infamous no-hair reputation. If matter gets caught in the chaos, swirling debris or a surrounding disk, the resulting particle beams could light up neutrino telescopes alongside gravitational waves. It's a long shot, but proving it would rewrite our understanding of how black holes interact with their environments. Every time these invisible messengers align, they paint a fuller picture of cosmic violence, one where space-time ripples and ghostly particles tell parallel tales. And as detectors grow sharper, we might soon find that the universe's loudest crashes whisper not just through gravity, but through particles barely heavier than a thought. Buried in the flood of data from gravitational wave detectors lies a needle in a haystack problem, finding signals so faint they're drowned out by Earth's constant vibrations, passing trucks, even quantum noise itself. This is where machine learning steps in, not just as a tool, but as a game-changing partner in cosmic discovery. These algorithms, trained on millions of simulated collisions, can spot patterns human eyes might miss, teasing out whispers of black hole mergers from what looks like pure static. One breakthrough came in 2020 when researchers fed LIGO noisy data to a neural network, a system modeled loosely on the human brain. Within hours, it unearthed 4 previously overlooked black hole mergers, events too subtle for traditional methods to catch. How the AI learned to recognize the unique chirp of colliding black holes, even when buried under layers of interference. It's like teaching a computer to pick out a single voice in a roaring stadium by memorizing the speaker's exact accent and rhythm. But machine learning isn't just playing cosmic Where's Waldo, it's reshaping how we interpret these signals. Take spin measurements. Determining how black holes twirl before merging used to take weeks of painstaking calculations. Now, AI models analyze waveforms in real time, estimating spins within seconds. Some systems even predict what doomed orbit the black holes followed billions of years ago, reverse engineering their fatal dance from faint spacetime ripples. The real frontier, teaching these systems to hunt for the truly exotic signals that don't match any known template. Maybe a neutron star collapsing into quark matter, or the faint tremors of a cosmic string snapping. Current algorithms are already flagging anomalies that defy classification, hinting at phenomena we haven't yet imagined. As detectors grow more sensitive, the data deluge will make human-only analysis impossible. But with machine learning as our co-pilot, we're not just keeping up, we're decoding the universe's secrets faster than Einstein ever dreamed possible. Gravitational wave astronomy isn't just for scientists in lab coats. Some of its most exciting breakthroughs are happening thanks to everyday people. From teachers to students to curious retirees, citizen scientists worldwide are rolling up their sleeves and helping uncover hidden cosmic collisions through projects like Gravity Spy. This isn't just busy work, it's real research where sharp-eyed volunteers sift through LIGO data to spot subtle glitches that machines might miss. Here's how it works. Raw gravitational wave signals are often buried under noise, false alarms from equipment tremors, cosmic rays, even footsteps near the detectors. Computers can filter out the obvious interference, but the tricky part: telling apart genuine cosmic events from weird, one-off artifacts. That's where human intuition shines. By classifying these noise mimics through online platforms, volunteers train AI systems to become smarter, speeding up the hunt for true signals hidden in the chaos. The impact is real. In 2017, Gravity Spy participants helped identify a strange zigzag pattern in LIGO data, a recurring glitch that, once mapped, made it easier to isolate actual black hole mergers. Other projects like Zooniverse's Supernova Hunters let volunteers tag potential neutron star collisions in telescope images that might have otherwise been overlooked. It's a global collaboration where anyone with an internet connection can contribute to cutting-edge astrophysics. What's truly revolutionary is how this flips the script on who gets to do science. You don't need a PhD to recognize an odd waveform or an unusual signal, just curiosity and a keen eye. Every classified glitch, every flagged anomaly gets scientists one step closer to cleaner data and faster discoveries. And as detectors grow more sensitive, that human touch becomes even more vital. So the next time you hear about a gravitational wave detection, remember, behind the scenes, it might just have been someone like you who helped make it possible. Detecting gravitational waves might sound like a clean, precise science, but the reality is far messier. Behind every cosmic collision LIGO hears, there's a minefield of earthly noises trying to drown it out. Forget black holes for a moment. Some of the biggest enemies of gravitational wave astronomy are things like distant earthquakes, rumbling trucks, even the lasers inside the detectors themselves. Take seismic noise, a minor quake halfway across the globe, ocean waves crashing on a beach thousands of miles away, or just a strong wind shaking LIGO buildings. All of them vibrate the ground enough to nudge the mirrors ever so slightly. That's why the detectors are suspended on elaborate pendulum systems, floating like feathers to isolate them from Earth's constant trembling. But some vibrations slip through, leaving fake signals in the data that scientists have to weed out like cosmic static. Then there's the laser itself, the heartbeat of LIGO detection system. Even the tiniest fluctuations in laser power or beam alignment can mimic gravitational waves. One notorious glitch, dubbed the blip, shows up as a sharp, unexplained spike in the data, lasting just milliseconds but baffling researchers for years. Some think it might come from microscopic dust particles zapping the laser, others from minuscule reflections inside the vacuum tubes. It's a reminder that hunting ripples in space-time means battling quirks in engineering down to the atomic scale. But the real curveball, wildlife. In one case, detectors picked up rhythmic disturbances that matched the footsteps of someone walking near the facility. Another time, acoustic sensors caught chirping crickets outside LIGO buildings, frequencies so close to gravitational wave signals that algorithms flagged them as potential cosmic events. Even the hum of airplanes overhead or logging trucks on a distant highway can send tremors through the ground, forcing scientists to become detectives of noise as much as explorers of space. Yet somehow, amidst all this chaos, the real signals shine through, those fleeting whispers from colliding black holes and neutron stars. It's a testament to human ingenuity that we can filter out an entire planet's worth of noise to catch vibrations stretching spacetime by less than a proton's width. Next time you hear about a gravitational wave discovery, remember, it's not just a triumph of astrophysics, it's a victory over Earth's endless symphony of distractions. Gravitational waves have taken us on an extraordinary journey, from Einstein's wild prediction to a revolutionary way of exploring the cosmos. Over these 30 discoveries, we've witnessed black holes colliding with the energy of a billion suns, neutron stars forging gold in their violent embrace, and even echoes from the universe's first moments. We've seen spacetime bend, spin, and ring like a bell, revealing secrets about dark matter, quantum foam, and galaxies billions of light years away. Each ripple in spacetime has rewritten the rules, proving that gravity isn't just a force, it's a storyteller, whispering tales of cosmic collisions, hidden dimensions, and the very fabric of reality itself. This isn't just science, it's a new era of discovery. We're no longer just observers of the universe, we're listeners tuning in to its deepest vibrations. And the best part, we're only at the beginning. With next-generation detectors on the horizon, who knows what else is out there? Wormholes, primordial black holes, or phenomena we haven't even dreamed of yet. So keep looking up, stay curious, and follow where these cosmic ripples lead. Because the universe is speaking, and thanks to gravitational waves, we're finally learning how to hear its voice. The next chapter of this adventure, it's yours to explore.